Hello everyone and welcome to Lecture 13. Today we begin our study of mathematical statistics. We'll explore variation series and their characteristics, the fundamental tools for organizing and understanding data. Here's our plan for today. We'll introduce mathematical statistics and distinguish it from probability theory. We'll define population and sample, then learn about variation series, both discrete and interval types. We'll cover frequency concepts, the empirical distribution function, and graphical representations like histograms and polygons. Let's begin by understanding what mathematical statistics is and how it differs from probability theory. In probability theory, we start with a known distribution and calculate probabilities of various outcomes. We use deductive reasoning, going from the general to the specific. In mathematical statistics, we start with data, observations from an experiment or survey, and we want to make inferences about the underlying distribution. This is inductive reasoning, going from the specific to the general, so probability theory is theoretical, going from distribution to probabilities, while mathematical statistics is practical, going from data to distribution. The key question of statistics is this: we have data from a sample and we want to make inferences about the entire population. This is what statistics is all about. Let me give you some examples. In opinion polls, we survey a sample of voters to predict the election outcome for the entire population of voters. In clinical trials, we test a drug on a sample of patients to determine its effectiveness for all patients with the disease. In quality control, we inspect a sample of products to assess the quality of the entire production batch. In all these cases, we're using sample data to draw conclusions about a larger population. Now let's define two fundamental concepts, population and sample. The population is the entire set of objects or individuals of interest. This could be all voters in a country, all items produced by a factory, or all patients with a disease. The sample is a subset of the population selected for study. We survey 1,000 voters, test 50 items from production, or include 200 patients in a clinical trial. The sample is what we actually observe and measure, while the population is what we ultimately want to understand. Why do we use samples instead of studying the entire population? First, the population is often too large to study completely. It would be impractical to survey every voter or test every product. Second, there are cost and time constraints. Studying a sample is much cheaper and faster than studying the entire population. Third, sometimes we simply cannot measure everything, for example, in destructive testing where the item is destroyed in the testing process. The key challenge of statistics is how to draw valid conclusions about the population from a sample. Let's look at how statistical data is collected and organized. Raw data consists of unorganized observations from an experiment or survey. Here's an example. Test scores of 20 students. The data is scattered and difficult to interpret. We need to organize it. The steps in data organization are: first, arrange the data in order, either ascending or descending. Second, group the data into classes or intervals. Third, count the frequencies in each class. Fourth, present the data using tables and graphs. The steps in data organization are straightforward. First, arrange data in order, either ascending or descending. Second, group data into classes or intervals. Third, count the frequencies in each class. Fourth, present the data using tables and graphs. This systematic approach transforms raw, chaotic data into organized, meaningful information that can be analyzed and interpreted. A variation series is a statistical series that shows how a characteristic varies among the elements of a population or sample. In simple terms, it's an ordered sequence of values of a variable, arranged in ascending or descending order with corresponding frequencies. Why do we use variation series? They organize raw data, reveal patterns, make data easy to understand, and serve as the foundation for further statistical analysis. Without organization, data is just a collection of numbers with no meaning. There are two main types of variation series. First, a discrete variation series, which is used for discrete data with countable values. Second, an interval variation series, which is used for continuous data grouped into intervals. Why do we need variation series? They organize raw data, reveal patterns, make data easy to understand, and serve as the foundation for further analysis. They are essential tools for any statistical analysis. Let's look at discrete variation series in more detail. This is a series where values are presented as individual, distinct numbers without intervals. Here's an example. Suppose we examine 20 samples and count the number of defective items in each. The table shows that 8 samples had 0 defects, 5 samples had 1 defect, 4 samples had 2 defects, 2 samples had 3 defects, and 1 sample had 4 defects. In this table, x represents the value of the variable, the number of defects there, and frequency represents how many observations have that value. To construct a discrete variation series, we identify all distinct values in the data, count how many times each value occurs, and present the results as a table. This is used when the data takes few distinct values with a small range. Now let's discuss interval variation series. This type is used when data is grouped into intervals or classes rather than individual values. Here's an example. The heights of 50 students grouped by height in centimeters. The table shows that 3 students are in the 150 to 155 centimeters range, 8 in 155 to 160 centimeters, 15 in 160 to 165 centimeters, 14 in 165 to 170 centimeters, and 10 in 170 to 175 centimeters. Each class interval has several components. The class interval itself, which is the range of values, class boundaries, which are the true limits of each interval, class midpoint, which is the average of the lower and upper limits, and class width, which is the difference between upper and lower boundaries. Interval series are used when data takes many distinct values or is continuous, like height, weight, or time. Let's distinguish between two important frequency concepts. Absolute frequency is the number of observations in a given class, denoted by F or N. For example, if 15 students are in a height class, the absolute frequency is 15. Relative frequency is the proportion or percentage of observations in a class. It's calculated by dividing the absolute frequency by the total number of observations. If 15 out of 50 students are in a class, the relative frequency is 15 divided by 50, which equals 0.30 or 30%. Relative frequency is useful because it allows comparison between samples of different sizes, it's easier to interpret proportions, and it's used in probability estimation. The empirical distribution function, or EDF, is the sample version of the theoretical distribution function f of x. It's denoted by f sub n of x and is defined as the number of observations less than or equal to x divided by n, the total number of observations. For example, with test scores from 20 students, the table shows the proportion of students with scores up to certain values. At x equals 70, f sub n is 0.10, meaning 10% scored 70 or less. At x equals 95, f sub n is 1.00, meaning all students scored 95 or less. The EDF estimates the true distribution function. As n increases by the law of large numbers, f sub n of x converges to f of x, the true distribution function. Beyond graphical representation, we also need numerical characteristics to describe data. Measures of central tendency describe the center of the data. The sample mean is the average value, the sample median is the middle value, and the sample mode is the most frequent value. Measures of dispersion describe the spread. Sample variance is the average squared deviation from the mean. Sample standard deviation is the square root of variance, and sample range is the difference between maximum and minimum values. These characteristics provide a complete numerical summary of the data. Measures of position include quartiles, which divide data into 4 equal parts, and percentiles, which divide data into 100 equal parts. Measures of shape include skewness, which measures asymmetry of the distribution, whether it's skewed left or right, and kurtosis, which measures peakedness, whether the distribution has heavy or light tails. Each of these characteristics provides a different piece of information about the data and helps us understand its structure. Let's focus on the most important numerical characteristics, the sample mean and variance. The sample mean is the sum of all observations divided by n. It represents the average value of the sample. The sample variance is calculated as the sum of squared deviations from the mean divided by n minus 1. Why n minus 1? This makes S squared an unbiased estimator of the population variance sigma squared. It corrects for the loss of 1 degree of freedom. The alternative formula for variance uses the sum of squared values minus n times the mean squared, which is often computationally easier. The sample standard deviation is simply the square root of the variance. It's in the original units, making it easier to interpret. Let's work through a complete example. Suppose we have test scores from 10 students: 72, 85, 78, 90, 68, 82, 76, 88, 79, and 84. First, we calculate the sample mean. We sum all the scores: 72 plus 85 plus 78 plus 90 plus 68 plus 82 plus 76 plus 88 plus 79 plus 84 equals 802. Dividing by 10 gives us a mean of 80.2. Next, we calculate the sample variance. We subtract the mean from each score, square the differences, sum them, and divide by n-1, which is 9. The sum of squared deviations is 522.4. Dividing by 9 gives us approximately 58.04. The sample standard deviation would be the square root of this value. The interpretation is that the average score is 80.2, with a typical deviation of about 7.6 points from the mean. Let me summarize what we've learned today. Mathematical statistics involves making inferences from samples to populations. We defined population as the entire set of interest and sample as a subset selected for study. Variation series organize data, discrete for individual values and interval for grouped data. Frequency is the count of observations in a class, and relative frequency is the proportion. The empirical distribution function estimates the true distribution function from data. Numerical characteristics include the mean, variance, and standard deviation. The key takeaway is that variation series are the foundation of statistical data analysis. They organize, summarize, and reveal patterns in data. That concludes our lecture. Thank you for your attention.